Welcome to the world of integral calculus. Today, we are exploring the washer method, a powerful technique used to find the volume of a solid of revolution. While the disk method works for solid shapes, the washer method is essential when our 3D object has a hollow center, much like a mechanical washer used in construction. Think of a single slice of our 3D solid. It looks like a flat ring or a washer. The area of this face is the area of the large circle minus the area of the small circle. When we multiply this area by a tiny thickness, dx, we get the volume of one infinitesimal slice. In a standard rotation around the x-axis, the outer radius is simply the distance from the further function to the axis, and the inner radius is the distance from the closer function. We must always identify which function is further away from our line of rotation to correctly define r and r. This is our master formula. By integrating from our starting point A to our ending point B, we are essentially stacking an infinite number of these thin washers together to fill the entire 3D space. The pi constant stays outside the integral because it is a constant multiplier for every circular slice. Geometry tells us distance is always positive. To ensure this, we always subtract the bottom coordinate from the top coordinate. If your axis of rotation is below your functions, you subtract the axis value from the function. If the axis is above, you subtract the function from the axis. Let's try a real example. We have the region bounded by y equals x squared and y equals x. We want to rotate this around the horizontal line y equals -1. First, we identify our bounds by finding where the curves intersect, which happens at x equals 0 and x equals 1. Now we define our radii. The line y equals x is further from our axis, so it forms the outer radius, r. The distance is x minus -1, which simplifies to x plus 1. The parabola y equals x squared is closer, so the inner radius, r, is x squared plus 1. We plug these into our formula. Our volume is pi times the integral from 0 to 1 of the outer radius squared minus the inner radius squared. Don't forget to square the entire binomial expression for each radius. Algebraically simplifying this now will make the integration much easier. After simplifying, we integrate term by term using the power rule. We evaluate the resulting expression at 1 and 0. Be careful with your fractions here, finding a common denominator is usually necessary to get the final precise answer. Subtracting the values gives us 7/15 pi. This represents the total 3D space occupied by the shape created by spinning the region around our shifted axis. Always include pi in your final answer unless asked for a decimal approximation. Consider an axis of rotation located above the region, for example, y equals 5. Now, the axis is the top and the functions are the bottom. The radius becomes 5 minus the function value. It is a common mistake to always put the function first. Remember, it's always top minus bottom. Visualizing these segments as physical sticks can help. The length of the stick is the radius. Whether the stick starts at the axis and goes up to the function, or starts at the axis and goes down to the function, the length is always the higher coordinate minus the lower coordinate. How do you know when to use the washer method? If there is a gap between your shaded region and the axis of rotation, you will have a hole in your solid, requiring the washer method. If the region is flush against the axis, the inner radius is 0, and it simplifies to the disk method. In advanced cases, your upper and the lower functions might switch places. If the curves intersect within your interval, you must split the volume into two separate integrals, redefining r and r for each section to ensure you are always subtracting the smaller volume from the larger one. One of the most frequent errors in calculus is squaring the difference of the radii instead of the difference of their squares. Remember, we are subtracting the area of the small circle from the large circle. Pi r squared minus pi r squared. Algebraically, these are very different results. Another mistake is forgetting the axis shift entirely and just using the function as the radius. Always draw the axis of rotation first. If it isn't the x-axis or y-axis, your radius expression must include that shift constant. Skipping this step will result in calculating rotation around the wrong center. To succeed every time, follow these 4 steps. Sketch the region and the axis to see the gap. Find where the curves meet to set your limits. Define your outer and inner radii by looking at the distances from the axis. Finally, set up and solve your definite integral with pi. Let's test your intuition. If we rotate the area between y equals 3 and y equals e to the x around the line y equals 4, which function is further from the axis? Since e to the x is less than 3 on the interval from 0 to 1, e to the x is further from the line y equals 4. The correct outer radius is for minus e to the x, because that curve is the greatest distance from our rotation line. The inner radius is the constant distance of 1, which is for minus 3. Using these in our washer formula would give us the correct volume. The washer method with shifted axes is just an exercise in careful geometry and algebra. By focusing on the top minus bottom rule for your radii, you can handle any rotation problem thrown your way. Keep practicing these setups, and soon they will become second nature. Generated by Vision Solve AI.